Hello and welcome, everybody. It's really great being here again. We have been here last year. And the session with Thomas before about Wi-Fi and showing all the different modulation scheme which was pretty cool. So we are now more on the optical side, not on the Wi-Fi side. So what we did is, so we only have, we have two now. So we are pretty excited because we are more coming from the optical side, the optical pluggable transceivers. My name is Thomas Weible, co-founder and CTO at Flexoptix, and together with Gerhard Stein, we used our latest development. It's a Flexbox 5. It's the programming device, but it's very powerful now, and we're really thrilled to show what we can do now in terms to analyze a transceiver with the capabilities of the transceiver. And that's actually, we show in theory, and also Gerhard will show some practical examples what we implemented. So in general, the presentation is separated in several sections. We do a little bit of recap at the beginning to get everybody on board, to know what we are talking about. And then we jump straight into the analysis we did with the transceivers, the tests. We have some dependencies on the bit error rate, but also looking at temperature and then later on the distance. And for sure, at the end, we do have a conclusion. So let's start with the SNR. And I don't want to mention that much on SNR, as Thomas already explained it quite well. Thank you very much for that in his workshop. And in general, you can say the SNR, like doing now this talk here in the audience, and some of you might use these translation intercoms. I am the noise level, actually, and while the translator tries to translate my English into Czech language, the SNR is not so good. For the ones who don't use the translation and listen straight to the English one, the SNR is a little bit better or slightly better. So you can really easily understand and detect the signal. And the same happens in Wi-Fi and also in optical environment. When you're coming more from the datacom side, as a network engineer, you are more looking on the bit error rate, and the SNR and the bit error rate, they are tied together. We do some recap now before we jump into what we did in the lab. So the recap is basically, I think I get over there. This one is flickering. I get over there. We did 2019 a presentation about 400 gig transceivers. Yes, they are already 5 years old. What is inside of a transceiver? And today we are mainly focusing on the DSP, the digital signal processor, which holds a couple of functions, and especially our thing is now the bit error rate tester, which can be done with the DSP and also measuring the OSNR or the SNR itself. For sure, there are other functions as well in there, like the forward error correction. We don't cover that in detail, not today. And so our lab setup, pretty straightforward. We used the Flexbox 5, opened it up, plugged in a transceiver, and we needed some external cooling devices. Otherwise, everything gets a little bit too hot. What did we test? 6 different types of transceivers, and the interesting test, especially on the temperature, we did with the 100 gigabit single lambda, the DR1, and also the 400 gig coherent transceiver, where we did the temperature tests, which are quite interesting. And now I hand over to Gerhard. He's going to show you the results now.
Thank you very much. Yeah, not all the results, but the most interesting one. And I know there's a very nice buffet at the end of this presentation. We need to rush a little bit, but please stay with us because we are going to blow up something, promised. But what kind of thing we are going to blow up, you will see. But first, let's talk about distances. So we have 2 parameters to keep in mind, distance and temperature. And with temperature, we are going to play around a little bit. But with distance, you have to consider one thing when you connect fibers. There are different type of transceivers you can connect, DR, ER, and so on. And you can pick one from our shop, for example, one which is specified for 40 kilometers. And of course, I also tried to run these out of spec. And the first challenge with this one, for example, was if we want to achieve 60 kilometers, it makes sense to take one that is specified for that. But if you connect the 2-meter fiber, you have to look for attenuators. Why? Because of the power. Transmission power and reception power is the thing here. If you just plug in a 2-meter cable, you might damage your transceiver. So always look for these tables, and what I calculated here was about 8 dB and up to minus 3 dB, which is the reception, basically. So I want attenuation of 11 dB, and now I tried different cables and connections. So with the cable drums, you can plug them in together, and you have different distances. And basically with that, because our main value is the bit error rate, what we want to see, what we want to analyze, and also understand how these transceivers react and what bit error rates you get, basically. And yeah, this curve is quite interesting because, as expected, have a look at the first three. They use the same attenuation of 11 dB, which I put on, which is when you want to be safe, as I showed you, you can do. But when you go beyond 20 kilometers, you should reduce attenuation because the cable itself also provides some attenuation, as you can calculate and check with the fiber drum. So by multiplying it, you have your natural attenuation. And yeah, the most interesting aspect of these curves are two things I want to show you. First of all, this red area, this red section, I just draw in with a 2.5 times 10 power to minus 4 as specified by another IEEE 802.3 this time. It's not Wi-Fi, it's Ethernet, .3 dB. And this is a bit error rate, which is still within the specification. And as you can see, with the 20 kilometers, we already are touching the limit here. If we go beyond, we can do this, but the bit error rate is out of that specification. And that is where I said, well, we need to reduce attenuation. But more interesting of that is, I mean, if I reduce attenuation, go to 40 kilometers, which improves because I reduced attenuation. More interesting are these jumps we have here. And the reason for why we have these jumps is transceivers with DSP try to control a little bit the bit error rate. They try to keep it constant, but on one hand. But on the other hand, it's difficult to implement control circuits there. So what they basically end up doing is using a lookup table. So look into what temperature is being set, and it triggers a different current that is being it is flowing over the laser and voltage. So there are some parameters that get controlled whenever the temperature rises, as you can see here. And yeah, it gets better with a higher temperature, but it starts getting worse again. So the best option still is keep it at low temperature. Anyways, what is bit error rate? Easy formula, basically. You have your bit rate, 400 gig, 100 gig, whatever, time, yeah, how many bits were transferred in total, and the number of errors. And you want to avoid this, so you could say one error is enough in order to see, well, if my first bit is erroneous, I can say this is my bit error rate. So if I transfer 1 gigabit of data and divide it by time and have one error, I get this. But you also have the Gaussian noise. So what is very common is to transfer 100 errors, because if your measurement is also wrong, you have a certain reliability. So there's some statistics going around. So a good rule of thumb that is usually taken is 100 errors. And with a gating time, normally we assume corrected bit error rate, because your transceiver also corrects these errors. It's a forward error correction. So a good value is 10 power at minus 12 you want to get. And if you transfer 100 errors, up to 100 errors with your certain reliability, with a reliability of 99%, that you will detect an error, and it's really an error that needs to be corrected or was not corrected in the end, you have a gating time of 16 minutes. Means if you have connected your fiber and wait 16 minutes, you have a probability of 99% that at least one erroneous bit was transmitted. And you know, of the other layers and protocols, you might have to do some retransmission, or if you have another layer where you can correct error, that is also possible. But if we don't do any correction, as you can see here within our specification, the 2.4, 10 power to minus 4, you get a gating time, which is way different. It's just 4 microseconds. My message to this formula and what we want to express here is, it's very important to correct your error. So this is a very generous value that is given by the IEEE. You still need to correct if you want to have a more reliable fiber. All right? So what did we do here? I would hand this over to Thomas, because we are going to repeat what we did last year, but not so much into the details. This is a coherent transceiver, and Thomas, tell me about it.
So basically, what Gerhard just showed was the 100 gig transceiver, a direct detection transceiver, the DR1. And now we took a coherent transceiver, a 400 gigabit coherent transceiver, and we're running it with cooler and without cooler. Nice side story here is actually the cooler. We took it out from a Cisco 800. A good friend of mine, he's a wrecker, and he disassembles all kind of gear around Frankfurt area in Germany. So if you need someone who does a proper recycling of server hardware, let me know. And this cooler actually, or this heatsink actually, did a pretty well job later on. And yeah, Gerhard will show what we got as a result.
So from direct detection to coherent, and we will play around with cooling as well. The coherent transceiver has a little bit of a different boot up time. It's usually between 30 seconds, 50 seconds, and take even longer to set up properly. And when it is set up, it usually goes into with higher temperatures. And since it consumes more watts in order to really create the signal we are going to send, because more properties are considered this time. What it does a little bit better, as you can see, we have constants here. So it's not affected so much by the temperature. And this is what you observe with cooling. But if we remove the cooling, which I also tried out, it didn't run for very long. But still, you have in the higher ranges, without cooling, when it boots up, it starts at above 50 degrees centigrade. You can see we have almost constant curves. So temperature does not influence that much a coherent transceiver, but what really influences is the distance, so how long your fiber is. This time we did not use attenuation because with this coherent transceiver it is not required, but be careful, it's a low power, it's not one of these 0 dBs. We have different coherent transceivers. With them, look up the specifications, if it is possible or not. But yeah, this was pretty easy to compare since no added attenuation was used here. Now let's get to the stuff we can blow up. So I wanted to find out how far we can get with our temperature. Usually when you plug in a transceiver, you can measure temperature through DDM, but you can also read two values which are warning and high alarm, which are about 70 degrees, and switch that read out this value and also reads out from the transceiver the current temperature should do something with the transceiver, because if it doesn't, the transceiver sacrifices himself, so it should shoot down. So we created a small software Python script where we were measuring that, and I wanted to see how hot this transceiver can get. And it's not that easy, because basically if you just run the transceiver and cover it in aluminium, I didn't do it here, but I tried it the first time, I went up to 80 degrees. So with this 100G transceiver, if you turn off the fans and remove the heatsink from your switch, it still can run. It still runs, it still reports values. It's not good, but it still can be used. So I wanted to find out if with 100 degrees, what happens to this transceiver. And yeah, I did this in 4 phases. So first one was warm up. I said like 65 degrees. We just let it running. It was not wrapped, just put it the foil. Below the foil, there is this flex box. So since it has a battery, we also have to protect it if we go into high temperatures. That's the reason why I ended at 120 degrees, because, I mean, it's a lot of temperature. But in order to get this, because the transceiver ends at 80 degrees and I want to get it even hotter, I used a heat gun, as you saw on the picture. So we have our warm-up here. Then I shut it down. I rebooted it and said, okay, software, up to 100 degrees, and let's see what happens. So it still goes up. The curve is a little bit more constant, so it goes into this direction, but the values are already bad. And it's just a 2-meter fiber, so yeah, you have low bit error values, obviously, but if you extend the fiber, as you saw in the previous diagrams, it just gets worse. So here the temperature has influence, as we said. With a current it would be different, but this is a direct detection transceiver. And after 100 degrees, I just shut it down, and we got this LOS. You'll see I did not plot what goes to 100 degrees because it's really a jump up and showing the whole graph. I wanted to show you the more interesting curves, which are these, because LOS means that it goes up to 1.0. Right? So imagine that, it's up here. That is what happens. After that, I cooled it down again. Third phase, I put a limit of 120 degrees this time, and it still worked. Yeah, it still worked, but it reached the LOS way sooner. So we have, if I zoom this small window in, like around 80 degrees, where it starts to show 1 of bit error rate, which means the signal is basically lost. The laser gets turned off in this case because it detects it's still too hot, but the ZDM is still working. The transceiver is still working, or working-ish. You cannot use it anymore for transferring data, but at least you can still read out the temperature. And does it get damaged? Well, I warmed it up to 120 degrees, shut it down, and let it cool down a bit. Turned it on again, and I got bit error rates again. So it was working again. The laser really turned on afterwards. So this is our cool down, and went up and went down automatically, so I wasn't heating up at all. But you can see there is a certain recovery observed here. So you can do this with the transceivers, but it's not a good idea. And just as a small takeaway, I might repeat this. High alarm and high warning are good values. Respect them. If you see these values and you get to this temperature, you should do something about it. Because you still can use the transceiver, but there's not a good margin anymore. So yeah, try to avoid it. What I also wanted to find out, because bit error rate, I mean, it's a rate you get, but what is happening internally? We are counting errors, at least on the transceiver side, but it reports bit error rate. So how does it count? To separate how the bit error rate is measured is not so easy to find out, because in the end you get this rate, and you're interested for, obviously, but there are many bits that get transferred. So is this stable? Well, I let the transceiver cool down. I used a different one for that experiment. And just for comparison, we go from 1 to 1.6. It's still by at minus 11, but it gets 60% worse in a very small range after 4 minutes. And if you leave it running for 1 hour, it gets stable. So reliably, you can say it starts with a low bit error rate, but it just started, so it's a little bit difficult. As you can see, you have some changes here, but it really locks here if you leave it running for 1 hour. So that is what the usual value is. Here I have a small quiz for you, a small question. It was a similar experiment, but what I did this time was, what happens if cooling system fails, if a fan fails, for example. In order to do this experiment, as you saw with the Flexbox, I just removed the heatsink and the fan, and observed what would be happening. And obviously, the red curve is the temperature. It goes up, as to be expected. This is a signal. Signal are step functions, usually. We'll get into this later, why it looks like steps. And the bit error rate is the blue curve. Now my question to you as audience, why do you think that when we put our cooler back after around about 30 minutes, here I remove it, here I put it back, why doesn't the bit error rate go doesn't go down like this value we had initially. It stays here and it like stabilizes a bit, but doesn't go any further. Any idea why this could be? Any other curve recovers itself. If I put the cooler back, temperature goes down as to be expected. Even the signal somewhat recovers, the optical signal, but the bit error rate keeps the same. Any idea why this happens? Because we have an effect of 10 times worse. Any idea? Raise your hands. No idea? Okay, I'll explain it. It's with a counter, because you can imagine it's like a rolling average. The history of how the bit error rate evolved is within this data. So what basically happens is the transceiver is measuring current bit error rate and takes the past one, just adds it, divides by 2, or depending on what interval is given, it's a little bit different, but usually it depends on the historical data. So you have a certain involvement with the bit error rate you should keep in mind. You can reset this counter if you do it while the transceiver is running. It is possible. It goes back to this value. But if you don't, you might think, yeah, but it doesn't recover. It's not true. It's just it has historical data inside. So now let's get to the exciting part. What time is it? Do we still have time? Ooh, okay, we need to rush this a little bit. What I'm going to show you is our new flex box. Here it is. And I'm going to blow up this transceiver. This was the transceiver that suffered the 120 degrees. So you will be judged if it still works. And I need to close this. Hope we can see what I'm going to show you. Now we get some flashy screens. Run me? It's not seen, okay.
No, it is.
Can we? Here we go. Awesome. So let me connect this box. Let's hope it does not blow up. If it would blow up, the values will blow up, but not the box itself. I'm not wearing any safety glasses, so, you know. It's just to keep you in. So, the transceiver is booting up. So this is one of our applications we are currently developing, and we want to integrate in our app ecosystem, where you have power meter and source, reconfiguration, OTDR. And this is a new feature we want to record. It takes a little bit of time. Let me check the logs. Yeah, but it's normal, like 1 minute or something. I'm very impatient today. Yeah, it's still booting up. There are different generators that need to be initialized. So you can, if you have used PRBS somewhere, you can set up different generators and judge them statistically. We usually use the default one, which is the PRBS 3.1, it is called, different coding schemes. And here you can see, it's working. It's not blowing up. So pretty warm here in our room. It warmed up itself. And you can see the temperature is rising because we have the DSP running. And you can see with our bit error rate, yeah, it jumps a bit. It's looking for its target value. And as you can see, we have step function here. That's the thing with our specifications. The semi-specification defines how to measure OSNR and decibels a little bit different. If the transceiver really has a signal of 23, 3, 7, whatever, here in the middle, you cannot display this value because it's a binary representation. So what it ends up doing is jump between these values. But after a couple of times, it stabilizes a bit, and whenever it changes, you see this jumps. It is because if you, how do you call it? If you get you can make this curve smoother, but it would be algorithmic. So we are being honest here and just showing whatever the transceiver is displaying, and that is what we get basically. And I'm not sure, I think it finished already. Could have been running for a little bit lower. Okay. Yeah, okay, it gave up. As I told you, it had to suffer a bit, but you could see the values, and yeah. So that is a tool we are developing, and later this year we want to show you. Thank you very much, and let's get to the rest of our presentation. and some. Welcome back. This is a video, in case we cannot show the live demonstration. And some takeaways for you, because it was a mouthful to digest. So bit error rate on direct detection transceiver depend both on temperature and fiber length, as you saw. There's some LUT lookup table that tries to correct it somehow, but there's still some dependency. Bit error rate is a rolling average, as you saw, with a recovery. And when we try to operate transceivers in very high temperature, it's not so easy to get these high temperature. It's hard to believe sometimes in data center, but 120 degrees is a different number. And as you can see, it still can recover. But there isn't a big margin between the high alarm temperature and when it really loses the signal. And with that, let me give some time to Thomas to talk about the other 3 bullet points.
Yes, and we also saw on the coherent one, and also this was really nice shown by Thomas in the Wi-Fi presentation. And it's quite very interesting that Wi-Fi and fiber optic are getting closer and closer together, although they are using a totally different media. The coherent technology itself is way more, I would call it stable or robust. So we use way more properties or characteristics of the light. We have a very powerful DSP with a very powerful implementation to recover the signal, and therefore it's more robust when it comes to influences like the temperature, for example. As written here, it's mainly the length which influences the coherent one, but not the temperature that much. To sum that up, also Gerhard mentioned about the bit error rates. Have a look at it in the IEEE, because that's quite helpful when you do your design and also establish your network and look on the counters. Bit errors will appear. It's not like in the 1 gig and 10 gig world any longer, where we don't have any bit errors or we don't see the counters. You will see them, but you have to interpret them properly and don't get confused when you see a lot of bit errors showing up. Because there is a forward error correction inside, which does help you to correct those errors. And finally, when your bit error rate at the end, when it hits the ASIC, when it's corrected, is fine. You don't have to bother much on the OSNR, which applies mainly for the direct detection transceivers, or the gray ones. For sure, OSNR needs to be monitored pretty well on coherent long-distance links, still like in the old, or still in the DWDM long-haul transmission part, where OSNR is a critical role. That's basically our part here in our presentation, to give you a wrap-up what we did in the last month. Thank you very much, and for sure we're going to be around today and tomorrow and take questions. Thank you.
Thank you.